Hi, let's continue our discussion of control systems by looking at an example. Um, in this example, I have a mobile robot steering system, and the dynamics of the vehicle is represented by this block. The position of the robot is the output of the vehicle, and the controller actually takes the difference of the actual position and the desired position and gives an input to the vehicle so that the vehicle goes in the position into the position that we want. Okay. Now what we want to do is we want to find out the steady state error of the system. To find out the steady state error of the system, we need to find out the uh, the error es, which is given as rs minus ys. However, this can only be done if we know ys, which is, as you would know, is gs over 1 plus gs times rs, right? Where gs is going to be this term multiplied by this term. So if you evaluate ys, what you get is k1s plus k2 divided by tau s square plus 1 plus k1s plus k2. So I'll leave you to actually evaluate uh, this output. And if you have this output, you can evaluate the error es as being tau s square plus s over tau s square plus 1 plus k1 s plus k2 rs. Okay, so that's the error that we have. And now what we want to do is we want to find out the steady state error of this system. So let me just clear off the screen a bit so that we can work a little bit more. Okay, now we know that the steady state error of the system is given by, is basically E of t, right? And E of t is given by E of t when t tends to infinity. So it's basically E of t when t is going to infinity. So that is equal to limit of s tends to 0 ses, which is equal to limit s tends to 0 s times es, which is tau s square plus s over tau s square plus 1 plus k1 s plus k2 rs. Okay. Now let's say we want to find out the steady state error when the input is a step input. So what we can do is we can replace the output that we have here by a over s. So let's say we replace it with a over s. Okay, and then we take the limit. So how, what would we get? We can cancel this s and this s here, and basically as you substitute s equal to 0, you would see that the steady state error et as limit t tends to infinity is going to be equal to 0. So this becomes 0, this term becomes 0, this becomes 0 and 0. So the denominator is non-zero, but the numerator becomes 0. So the steady state error becomes 0. Okay. Now, so that's for a step input. Now what happens if we have a, let me just go back in this slide, just erase this, and let's take a look at what happens when you have a ramp input. So a ramp input is given by a over s square. So you have one cancellation here, and the s here also cancels here. So you get a 1 here, right? So if you, for a ramp input, limit t tends to infinity et is going to be what? So substitute s equal to 0 here, so you get 1, and the denominator becomes, this becomes 0, this becomes 0, and you get k2. So the error, the ramp error, the steady state error for a ramp input is 1 over k2. Okay. Now if you had a parabolic input or acceleration input, then you would have had s cube here. In that case, what would have been the error? In that case, you can see that there would have been an s here as a what should I say, as so there would have been a s in the denominator, and as we evaluate the limit as s tends to 0, this is not going to cancel out, and therefore the error is going to become infinite.